Good morning, Physics 20. I hope you guys are doing well today. Welcome back to our next lesson. And today we're going to be looking at graphing accelerated motion. So, lesson subtle hint on test. Your next quiz is going to have 2 pages of graphing questions at least. Okay, so there's lots of graphing on your quiz. So study this, and I even at the end of the set of notes, there's going to be essentially a study this page sheet, so which will have all of the summaries of everything you need to know for graphing. Okay, so once again, this is July while I'm filming this, so I have no idea what September is even going to look like. So when I say on your quiz, I'm assuming that we're actually back in school and having quizzes. If it's sometime and we're still learning at home, I don't even know what's going to happen. So when I say on quiz, I mean assuming there is going to be a quiz. So study that stuff. It's important. It's on your assignment too. That you will have, regardless of where we are. All right. So enjoy the pun. It's good. Must happen. Star Wars. Epic. All right. Okay, guys. So we're going to leap right into it, and we're going to be looking at how to draw these graphs for accelerated motion. Now, remember, when motion is accelerating, the distance that is being covered is going to increase as time is going on. It's not like 5 meters every second. Well, you may be going 2 meters a second, and then you're going to speed up, and then you may go 4 meters a second, and then you may speed up again, and you'll be going 6 meters per second. Okay, so as you go on, the distance covered is going to be increasing exponentially. Okay, so on a distance time graph, there's not a lot of math we can do acceleration-wise, but you gotta know the pattern. Okay, so when you are going to be speeding up, the distance that is going to, or displacement, okay, it could be either distance or displacement, is going to be increasing exponentially. So this guy here, this red line, is our speeding up or going to be your positive acceleration. Okay? Okay. Well, what's the other type of acceleration though? Slowing down. We can slow down. So what that means is that we can have negative acceleration. We can still be going forward, but you're going to be slowing down. Think about what that would look like. Think about how much distance your vehicle is covering as time goes on when you got your foot on the brakes. How would you draw that as a graph? It's going to go curve downwards, okay? So if you're slowing down, it's going to look something like that, okay? So notice the distance that is being covered is curving downwards in that logarithmic style, okay? That opposite of exponent, okay? Exponential growth. So what we've got here is we've got our slowing down, which is also your negative acceleration. So that's that blue line there. Okay. So I'm assuming you guys have these notes out in front of you and you're already drawing this stuff in there, right? Yeah. Yeah. Okay. So that is the patterns that you are going to need to know for a distance time graph when we're dealing with accelerated motion. There's not any math I can really get you to do there, at least at this point in Physics 20. So, but the next graph, there's 2 types of math we can do on this one. Yeah, my computer, scroll down. All right, so on a velocity time graph, we have acceleration is going to look a little different. Now, once again, watch your axes. This is the biggest mistake that I see, guys, is I see distance time graphs being treated like velocity time graphs. So watch these, guys. Really pay attention to your axes. Really, really, really read those carefully. Don't get caught up in one graph having to look similar to the other. The distance time graphs and velocity time graphs look completely different. Take your time with them. Ask questions in Focus or on Google Meet or however we're doing extra help here. This is a really, really tough topic, and take your time with it, okay? Okay. So for a velocity time graph, let's think about what acceleration means according to your distance. Or your velocity, excuse me. What does acceleration mean with your velocity? Your velocity is going to be increasing over time or changing over time. So if you're going to be accelerating, your velocity is going to increase over time. Now remember, we said uniform accelerated motion. That means your acceleration is uniform. So your velocity, now once again, straight line, guys, please use a ruler. It's a pain in the butt to use a ruler on this thing. I have to lay the whole computer flat and draw on the touch screen of the Chromebook to use a ruler. It's a real nightmare. I think I did that. Yeah, you saw me doing that in an earlier video. It was kind of nutty, actually. Okay, so this blue line is what speeding up or positive acceleration is going to look like. Your velocity is increasing as time goes on. Okay, well, what would slowing down look like on a velocity time graph? Opposite direction. Okay, so your velocity is going to be decreasing over time. Okay, so this blue line is going to represent slowing down or negative acceleration. Okay. So, ladies and gentlemen, there's a couple of different things that we can do here to calculate directly off this graph. And I am going to be asking you to do this on a test, lesson subtle hint. And if, because of COVID, there is no test, it will be on your assignment, I promise you that much. So, pay attention. Write this down. So what we got is two things that you 100% need to know. And that is, remember from our previous setup with velocity time or distance time graphs and velocity time graphs for uniform motion, you can use your slope for stuff. On a distance time graph, your slope was equal to your speed. However, look at your axes here, guys. We've got velocity over time. So remember that your equation to your slope, and in y equals mx plus b, that's m. And that is your change in y, so your y2 minus y1, divided by your change in x, so x2 minus x1. Okay? Well, in this case, ladies and gentlemen, what does our slope tell us? Our slope is the velocity, and our x is the time. Okay? So hold on a sec, guys. I got an important phone call coming in. It is the weekend. I'm going to pause this and I'm going to come back. All right, guys, I'm back. So we were talking about the slope and why that is significant. Okay? So look at your axes. We've got velocity over time. We've got velocity on the y and time on the x. What equation does that look like? Very, very similar to your basic acceleration equation. So when you've got your acceleration is equal to your v2 minus v1 over your change in time. Well, look at this. Velocity over time, y over x. Velocity over time, y over x. So what you've got is if I give you a graph, a velocity time graph, and I say, what is the acceleration? You need to calculate the slope. Okay? That is ultra, ultra, ultra important, guys. Okay? Lesson subtle hint. On test, on assignment. If I give you a graph and I say, and it's a velocity time graph, and I say, what is the acceleration? You must calculate the slope. You must show me your work in the form of slope. If you go acceleration equals v2 minus v1 over delta t, I'm not giving you points. Okay? You have to use the slope. If you use acceleration equals delta v over delta t and don't show me you're using slope, I'm not giving you any points because it's the wrong strategy. Okay? It's the wrong equation. It's very, very important that you guys make that connection with as soon as I give you a graph and you're calculating stuff directly off a graph like that, you have to use your graph equations. It's going to become even more important next year in Physics 30 when I start giving you guys these big, intense graphs and you're having to algebraically use y equals mx plus b in order to get stuff out of there. So another data off there. So this is just the starting point for what we get out of it later, okay? And on university, graphs will be your life. Biochem and physics, graphs will be your life, okay? Bio and physics especially. So skills now, we're teaching you now, will benefit you later. Cool beans? Cool beans. So if I ask you to calculate the displacement off this graph, remember, there's two different things that you can calculate with a graph. You can calculate that, at least at the Physics 20 level, is we are going to be looking at your area and your slope. So remember how we looked at area earlier? Well, area is either lengths times width for a rectangle, or it is going for a triangle, you have base times height over 2. Okay, so those are two area equations. Let's do the same process again, and let's think about what the area could mean on a velocity time graph. Now, if I ask you to calculate the displacement on this red line here, well, we would need the area between the x-axis and the end of this line here. Well, we've got two shapes. We've got area 1 and area 2. Now, if I'm going to be finding this area 1 here, what would I have to do? Length times width. So we've got length, we've got width. Length times width. Velocity times time. So if I have change in velocity, so I would have the velocity here to velocity here, that's a delta v right there, and I am multiplying that by my width, which is a change in time. What does v times t give you? Displacement, guys. Will you look at that? Okay, so it's super important, guys, that you need to recognize these connections. It's so much easier to determine what equation you need to use off a graph if you can recognize the connections between the axis and the equation as to just memorize, okay, on a velocity time graph, I need to use slope in order to find acceleration. And then read that 1,000 times and memorize it. See, that's not going to help you as much as if you can see those connections with the axes. Trust me on this one, because you've got, like when we scroll up, well, you've got multiple patterns to recognize and memorize on a distance time graph, and then multiple patterns on a velocity time graph. And guess what? I'm going to introduce another one on acceleration time. So that's just a lot of stuff just to memorize. So my advice is don't just memorize things when you can learn a pattern. And by learning a pattern or a strategy and memorizing just that pattern or strategy, you could apply that pattern or strategy to a dozen different scenarios. And it's not going to fail you. Right? That's what I did in university. The second there was a pattern or a strategy, I'd learn that and then apply that to the case. And it worked. Okay, so that's my advice. Take it or leave it. You guys are almost adults. Listen to me or don't listen to me, but trust me, it's going to work out so much better for you guys if you learn the pattern and not just memorize. Okay? Okay. The other advantage of that too is it gives meaning to what it is you're looking at. And eventually over time, you'll just probably memorize this stuff anyway. But if you understand the meaning behind the strategy you're looking at, it's a lot easier to actually remember as opposed to just these random patterns that you're trying to memorize with no context. So learn the pattern, your life will be so much easier. Okay, guys? Okay. So our last pattern here, ladies and gentlemen, is we have our acceleration versus time. Now, we're going to spend like very little time on this graph because we can only use it in one scenario here. So because we are looking at uniform acceleration in physics 20, you're going to see your acceleration going to be constant. Okay, we are not going to be looking at increasing acceleration or decreasing acceleration. That's beyond the scope of the curriculum. So there's no objectives for that. So we're not going to get into that bit. It does happen. Absolutely it does. Anyone who drives a car knows you can have changing acceleration, right? So we do it all the time. But the math for it just isn't in physics 20. So because of that, this is the pattern you're going to have. You've got your acceleration versus time, and if this is, 5 there, it would be accelerating at 5 meters per second squared. Okay? So in this case, for that red line, well, what I could ask you to calculate, okay, well, what would be the velocity of this? How would you use that? Use that strategy, guys. Use that strategy I just told you guys. Look at your axes. Well, acceleration times time. Okay. Well, I can't calculate the slope of, I could calculate the slope of a flat line. Well, slope is 0. It's not really going to help us. So, but I can look at acceleration times time. Well, acceleration times time, what does that give me? That gives you your velocity. Okay, so all that is here, ladies and gentlemen, is just rearranged of A equals your delta V over your T. So this is just rearranged of this. Well, what equation, area or slope, best fits this? Area. So if I give you an acceleration time graph and I ask you to calculate velocity, calculate the area. On a test, lesson subtle hint, I'm most likely not going to give you acceleration time graphs because there's so little we can do with them. But I guarantee you, I promise you, you will see position times graphs and velocity time graphs, and you will need to calculate area and slope off of at least one or both of them, as well as determine the patterns of what is happening. Okie dokie? Okie dokie. All right, so we've spent a lot of time on that one particular page. Let's go and start looking at interpreting some of these graphs. All right? Okay, so what I'm going to do is I'm going to give each of these graphs a particular stage. We'll give them a letter, A, B, C. Okay, so I have this particular stretch of motion A, this stretch of motion B, this one C, this one D, that E, that F, and then I'm going to add 2 more. And we're going to go boink, kind of like that. That curves in too much. There we go. And then I'm going to add another one. That's going to go like that. Okay. So I'm going to call this guy G and that guy E. Let's actually try this again and get my alphabet correct. I can't even say it's Monday. It is actually Friday. There we go. Okay. So, ladies and gentlemen, we're going to determine the pattern of motion of each of these. So what is the first thing you need to do when you look at a graph and you're going to go to determine its motion? look at the axes. So come over here, look at these axes, ladies and gentlemen, and then you need to put your head into the thought process of a displacement time graph. And you need to think in the context of displacement time. Okay? All right, so once you've done that, let us go and look at rest. Okay? So, because the question here is asking you to describe the type of motion and the direction of each of the following sections. So, let's look at some of the different types of possible motion we could have. So because we have repeated motion and various ones, I'm not going to go A, B, C, D, E, F, G, H. I'm just going to look at the patterns of motion and tell you which ones they fit into. Okay, so let's look at rest. Now we're thinking here, position time or displacement time graph, position time graph, distance time graph. For this guy here, rest. When you're at rest, think about the position. Does your position change? No, your position stays the same. So right now, I'm sitting in my desk chair. I'm not moving. Nope. Is my position changing? Nope. If I move closer to my desk, well, the other side of my desk, it's an L-shaped desk. So if I move closer to this desk, and now I'm sitting here, is my position changing? Nope. Still not changing. So is my position different than when it's here in front of the Chromebook? Yes, it is. The position's different. But was I moving in either case? No. So on a displacement time graph, we need to, for when you're at rest, you need to look for times when there is no change in position, a flat line. So where do you see flat lines here? B and D. Okay, so we've already looked at those in our previous video on graphing for uniform motion. Okay, so that should be a review for you. And now let us go and look at uniform velocity, so constant motion. Okay, so we have uniform motion. Well, where's uniform motion on a displacement time graph here? Let's go uniform motion forward, actually, because we have to have direction as well. So what is uniform motion going forward here? A and C. Good. How do you know? Because the displacement is increasing. Okay, and it's going in a positive direction here. So here's if we're going increasing here, this is 0, this is the starting point. Well, you are increasing your displacement as time goes on, and it's a nice flat line. It's doing so constantly. Now, which one's faster, A or C? C is faster. Why? Slope is steeper. Okay, so C is faster because of the larger slope. Okay. Yes, you need to know that too. Lesson subtle hint on test. Okay. Another tip, ladies and gentlemen, whenever I say lesson subtle hint, it's actually on your test. Years ago, I had a student who organized in her notes different sized stars for how dramatic I was with lesson subtle hint. And every time I said lesson subtle hint, she would put a star in her notes. And if it was, just lesson subtle hint and then carry on, she knew it was a minor thing that'd be on the test. Whereas if I went completely ridiculous and goofy and crazy and wild and said, lesson subtle hint, put a big star. Yeah, she rocked my exams. So lesson subtle hint, when I say lesson subtle hint, it really is on your test. I'm not lying. I'm essentially like giving you a study guide. So pay attention. All right. So, ladies and gentlemen, let's look at uniform motion backwards. Now, when I say backwards, I don't mean like doing the Michael Jackson moonwalk and actually walking backwards, although you could be doing that. But we're talking negative direction. Okay, so if in this particular case, east is the positive direction or the forward direction, then west would be the negative direction. So what is uniform motion, but going in that opposite direction, that negative direction? Good, D. How do you know it's uniform? The displacement is changing constantly, continuously, seen by that straight line. And how do you know it's opposite direction? It's moving closer to the word zero. It is moving away from that positive direction. All right? Okay. So the next piece we're going to be looking at is, let's look at our acceleration. Okay. And now there's different types of acceleration. Remember, there's positive acceleration and there's negative acceleration. And you can accelerate in the, quotes, wrong direction too. So here, let's say acceleration. So we're going to say positive acceleration in a positive direction. Okay, so you are going faster facing east. Which line is that going to be? F. Okay, how do you know? It's curving upwards in that easterly direction. Okay. Okay, so we've added a couple of more on here just because we can. We have G and H left. So let's look at what each of these are. Now, look at G. That's a weird shape. Okay, what would G be? So go back and have a look at that graph again. What is G doing? It's curving, accelerating in the negative direction. Okay, so G is going to be positive acceleration in a negative direction. So that would be going faster west in this case. Well, what about H? What's H doing? Slowing down while going a negative direction. You can see that curvature indicating slowing down. Okay. G is one you're not going to see a ton of. Okay. But at least in Physics 20. Oops. Okay. All right, guys. Make sure you have those notes down. Good page to study from. All right. Yeah, you're going to see test questions on some of that stuff. Hint, 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 hint. All right, so what we're going to do now is we're going to go and look at a velocity time graph, and we're going to talk about some of the different patterns and math that you can do on these things. Okay. So, at what times does an object come to a stop? All right, step one. The second you got a graph question, the first thing you're going to do is look at the axes. So you're going to come here and you're going to look at velocity time. Okay, we're different graph now. The previous question was a displacement time, D versus T. We're now looking at V versus T. Change your brain organization, change the focus, and think about velocity time graphs. Okay. When you're thinking velocity time, you're thinking about how fast stuff is moving. It's a vector, so you're thinking about direction. You're thinking about how fast something's going. Okay. So at what time does the object come to a stop? Now think about what stop means. Okay. We're thinking velocity. When we're stopped, do we have velocity? No, we don't. When we're stopped, our velocity is zero. This is a velocity time graph. Where do we have zero velocity? 6 seconds. Okay. So, ladies and gentlemen, 6 seconds is when the object comes to a stop. Now notice how I have time bracket S in these questions, and on your test you'll have that too. It means I want all times that that object is stopped. That means there could be one or more of them, and I want them all. All right, sometimes there might be one, sometimes there might be more than one. In this case, there's only one. Okay, now what would be the most common mistake that I would see on this? The most common mistake on this graph would be I would see 4 to 5 seconds. Why is 4 to 5 seconds wrong? Because at 4 to 5 seconds, this stretch here, the stretch on Y, when you read over, that object is moving at 20 meters per second. Okay. The flatlining bit is on a distance time graph. That's why I told you to get your brain into velocity. So, and it's honestly, it's easier to read the graph than to simply memorize patterns. Okay. Trust me on this, guys. It's better to read the graph and use your graph reading skills than to memorize patterns. Okay. Because if you're memorizing a pattern with no context, you're going to have a really tough time, and it'll be so easy to get the graph switched. So trust me on this one. Learn the patterns of the graphs and read those axes. Okay. All right. So does the object change in its direction in motion, and if so, at what time? Well, remember, think back to our previous video. When changing in direction happens on a velocity time graph, when does that happen? When you cross that x-axis. Because here, well, all right, well, our velocity is increasing. Well, our velocity is now decreasing. Our velocity is decreasing. When you have decreasing velocity, that means you're slowing down. That doesn't mean you're going backwards. Okay, so when you have a negative velocity, that is going in the opposite direction. So this guy has no direction change. Okay, because he doesn't cross that x-axis. Okay, so we talked about that in the previous graphing video, so that's super important. Watch for that. Think about your velocity time stuff, okay? Think in the concept of velocity. At what times is the object at constant velocity? Okay, so let's come back up at our graph, and we're thinking constant velocity, velocity time. So if velocity is constant, that means velocity is not changing. Where is velocity not changing on this graph? Why? It's that 4 to 5 second range. When you read this, it's over at 20 seconds, or 20 meters per second, excuse me. All right. Oops, I skipped over C. That we're going to look at, or we'll answer D here. It says what times. So please don't write why. Why isn't a time? That's a section on the graph. It is 4 to 5 seconds. That's the answer that I want. Okay. So I won't take off points. If you say section Y, it'll just make me cringe because the question says time. So anyway, don't make me cringe, please. All right. So you also, guys, you may also wind up with a really, really picky university prof who would insist on stuff like that. I've had profs like that before. You guys notice I'll very often circle positive and negative signs. I had a prof who deducted points in university in organic chemistry if you did not circle your charges. To clearly communicate what was positive and negative, you had to do these complicated drawings and mechanisms and what have you, these organic chemistry reactions, and the charges are super important. Well, how does he know that this little dash is actually a negative sign, or if it's just a missmudged pencil mark, right? So yeah, so you had to circle your charges. To this day, I'm still terrified of losing points on that. I was like, maybe like 15 years ago now. I'm getting old. Okay, guys. So our the question we have is, when is this graph slowing down? So remember with slowing down, that means our velocity is going to be decreasing. So where in this graph are we having a decrease in the velocity? Good, 3 to 4 seconds and 5 to 6 sections, or sections X and Z. Okay, so that is where you can see, all right, here's my velocity. The velocity is going down. Here we go. Here's my velocity. The velocity is going down. Okay, so that, ladies and gentlemen, is your sections X and Z. Okay, so sections X and Z, and just so that way I am not cringing at my own notes, I'm going to write down the appropriate time. So times 3 to 4 seconds. And because the question does say time, and then 5 to 6 seconds. Okay, so 3 to 4 seconds and 5 to 6 seconds. Cool beans? Cool beans. All right, calculate the acceleration at 3.5 seconds. Okay. So, ladies and gentlemen, let us begin. Where's 3.5 seconds on the graph? Okay. Well, 3.5 seconds is right here. What do you need to do when I ask you to calculate something directly off a graph like this? What are your two possible strategies? Slope, area. Let us figure out which one we need to use. Tough one. So, ladies and gentlemen, you need to calculate the slope. Why? Okay, let's go through the thought processes that you need to do to determine how I got to slope. So, I need to calculate the acceleration. I have velocity and I have time on my axis. So, I'm going to compare these equations here. For this one, I'm just going to do my math on the side. This is going to be easier here. So on your notes, you guys can actually write this down under E. So that way I'm not scrolling up and down on the screen without being able to look at the graph. I'm going to just do my, my notes here and calculations for E right up here. Okay. So I can look at, if I go velocity times time, well, that doesn't equal anything. For our case, for what we need, that's displacement. Velocity times time is displacement. I don't want displacement for this question. I want acceleration. Well, I've got velocity over time. That's better, much better. So if I have got my change in velocity over my change in time, that'll give me the acceleration. Well, I have the options of slope and area. Well, slope is my delta y over my delta x, and area is length times width. So which one fits when I want this guy? Slope. This guy more closely matches this guy. Velocity over time will give you acceleration. So you must calculate the slope. Okay, if I see 35 over 3.5, you're not getting points, okay? Because that 35 is that instantaneous velocity at that point. You need to have the slope of that line. So my advice with getting slope off a graph, pick 2 points that are the farthest apart as possible that are the easiest to read. Well, this is a really, really easy to read graph. I'm going to pick these 2 points here. You know what? Instead of dots, I'm going to just write them as X's. So then that way it's easier to identify the points I've picked. Okay, I'm going to pick that point, and that point, because they're the farthest possible point and they're easy to reach. Like they're right on the grid lines. Always pick points right on your grid lines if possible. So much easier. Okay. Well, I need to calculate my slope, which is equal to y2 minus y1 over x2 minus x1. That is a slope. And you can even write your acceleration is equal to slope like that. Now, y2. So I'm going to go look at my second point. This, ladies and gentlemen, when you're going to be picking your points as to which is the first and which is the second, your first point is going to be the one closest to 0 on the x. So that is going to be 0.1 and that is going to be 0.2. Now, notice we're slowing down here. Yes, you're going to wind up with a negative number, and that's good. You want a negative slope because that shows you're slowing down. If you have a positive slope, something went wrong. So y2, this is my point number 2, and the y is 20, and my 1 is 50. Okay, that's going to give me negative 30, and that's okay. Now my x for 0.2 is 4, and my x for 0.1 is 3. So therefore, my slope, which is equal to my acceleration, is going to equal negative 30 divided by 1. Okay? Okay. So, ladies and gentlemen, well, negative 30 over 1 is, well, negative 30, which equals my acceleration. If I see this, there are two things I'm going to be deducting. Where will you lose points here? Units? Direction. This particular question on the graph, I did not say how many sig digs I want. On the graphing questions on the test or assignment, I will tell you how many sig digs I want you to round it to. And most of the time, it's going to be 2 sig digs. I will say round your answers to 2 sig digs, which means you have to round your answers to 2 sig digs for full points. So let's assume I said 2 sig digs. Well, this is 2 sig digs. For your final answer, I said, what is the acceleration? Acceleration's a vector. I need to have direction on this, guys. No direction and you're losing points. Okay, direction is super, super important. So 30 meters per second squared, because that's the units for acceleration. And what does this negative sign tell us? That the acceleration is going in that opposite direction. Which means you're slowing down. Okay? So it is opposite direction. It's going backwards. The acceleration is backwards, which means you're slowing down. Okay? So then you are going to please either box or underline or somehow communicate to me that that's what you want me to mark. Cool beans? Cool beans. All right. So last question we got here. What is the distance traveled during the first 3 seconds? Okay. Now, distance traveled in the first 3 seconds. Well, there's 3 seconds. Now, this is going to be the same type of thought process that we did earlier. I'm asking you to calculate something directly off the graph here. You got slope and area as your possibilities. So, I've asked for distance traveled. Distance traveled is v times time. Look at your vectors here. Velocity times time. V times t equals distance. Area is length times width, or for triangles, length times height over 2. You need to calculate the area. So you're going to draw a line here at 3 seconds, and you're going to calculate the area of everything between that line and that x-axis. So the best thing that you can do here is break this into two possible shapes. I'm going to call this area 1 because I can, and I'm going to call this area 2. Now, once again, I'm going to be doing my math up here just because it's easier for the sake of the video. I'm going to erase this stuff, and you guys can write your work for this under the actual section of your notes there. But just so I'm not scrolling up and down and up and down and up and down, you can't even look at the graph while doing it, I'm just going to do the math here. For that last one, which is F. Okay. So, ladies and gentlemen, what is my next thing? What should I do first? Calculate the area. I'm going to do area 1 first. So area 1 is this guy here. 0 to 10, well, that is 10. 0 to 3, that's 3. So area 1 is going to equal length times width, which is going to equal 3 times 10, which is equal to 30. Okay. Now, let us look at that triangle. My area 2, well, that's a triangle. That's going to equal base times height over 2. Well, let's look at the base. So we've got the base 0 to 3, 0 to 3, so that base is 3. Now let's look at the height of this triangle. The most common mistake that I would see for something like this would be 50. Why is 50 wrong? Why is 50 not the height of this triangle? Because it's not starting at 0. Here, this triangle shape starts at 10 and goes to 50. So that means the height of the triangle is 40. Okay? So be very, very careful with that. That's the biggest mistake I see on these graphing questions when and finding the area is not reading those axes properly to get your scale there. You get that length of that side. So watch where it starts. Okay, really watch for that. So this is 40. So you are going to have 3 times 40 divided by 2, which is going to get you your area. Okay, so that would be 120 over 2, which would be 60. Okay, so your area total is going to equal the distance. Now, in the question, I said distance. So, ladies and gentlemen, that says scalar. Do I want direction here? No, I don't. No direction on scalar quantities. So, you add the two together, 30 plus 60, and your area total is going to be 90 meters, which is going to give you the distance covered. Okay, I still need units. I still need sig digs. And in this case, I would give you the sig digs that I would like to see. Okie dokie. Okay. I know this graphing stuff is super tough, guys. I know it's a lot. I know it's overwhelming. And this is going to be a really long video by the time I'm done filming here. But definitely spend time with it. Do some of these practice problems down here. Get comfortable with the graphs because graphing is not going away, guys. It's coming back in Physics 30. You're going to be doing graphing as long as you're doing physics. And in university bio, there's tons of graphing. Tons of graphing. Anything in science you do, you're graphing it. So you want to really be comfortable with these graphs. Okay. So those are practice problems. Do some of those. Now this is your review page. I'm going to put a big star and I'm going to say, study this on test. This is the page in which you are going to come to begin your studying of graphs. This is the list of things you must know and the patterns that you need to know in order to succeed in graphing questions in Physics 20. Put a sticky note on this page so it sticks out of your notes with a label that says study this. Spend time with this page. Know the stuff on this page. Remember your access reading skills. Lesson title hint, study this page. I'm giving you a study guide for the stuff you need to know on graphing on this page. Cool beans? Cool beans. All right. So, ladies and gentlemen, what we've got on your beautiful study page is going to be the most awesome thing here. Sorry, I've got two computers going. I got this computer. I got the Wacom writing tablet I've borrowed from Mr. McLeod, and I got my regular computer here because I forgot all my notes at school. So I'm just kind of doing my computer copy of the notes. And now I can't rotate this because this is sideways. And now I'm fighting with this. There you go, rotate view. There we go. Okay. So much easier to have your work done in advance when it comes to filming. It's like preparation, so you're ready to go. So I make fewer mistakes because then I'm focusing less on all this, on all the actual doing the math because I've already done it. So anyway, it's good. Makes for better film, better videos. Okay, guys. So for uniform motion, distance, time, velocity, or displacement time. Okay, you are going to see patterns that look like this. Okay, uniform motion on a distance time graph looks like this. I'm also going to draw a blue line here, and this blue line is going to show stationary. Okay, so then when you have these two things, this means when you're not moving. Okay. All right, so that's stationary, and this is in a positive direction. And I'm going to switch colors again, and I'm going to go to green, and I'm going to do this guy here, and that guy is going to be in a negative direction, so you're going backwards. Okay? All right. On a distance time graph or displacement time graph, you are going to have your accelerated motion looking like that. This is positive acceleration, so you are speeding up. The blue line is going to look like this. That is negative acceleration. You're going to be slowing down. Okay. So when on a distance time graph, remember your slope is going to equal your delta y over delta x. And on this graph, you can calculate the slope. Okay? So your slope is going to equal your delta d over your delta t, and that's going to equal your velocity. Okay? So slope equals your velocity, your change in velocity. Okay? We do not calculate area on a distance time graph because, well, area, distance times time. Oops. That should be a capital A for area. Well, is that useful to us? No. Okay, we do not use area on a distance time graph or displacement time graph. Cool beans? Cool beans. Write this down. Like, pause the video and write this down. You don't have to rush to keep up with me. This is video. Pause it if you need more time to write. All right. Get it? All right. Time to write. Yeah. Okay. Velocity time graph. For uniform motion on a velocity time graph, you can have a line like this. Okay. You know what, guys? I'm actually going to make this a bit shorter so I can squeeze more stuff on in there. So this red line is going to be positive direction. Okay. Then if we jump down here, this blue line, what does that blue line mean, guys? That blue line is stationary. You only have, on a velocity time graph, when you have zero velocity, that's when you're stopped. Okay. Now this green section here, I'm going to write that actually in purple, this bit here, that when you cross that x-axis, that is a change in direction. And then this green bit is going to be negative direction. Okay, uniform velocity going backwards, a negative direction, opposite direction. Okay? Okay. Accelerated motion on a velocity time graph is going to look like this. Okay? So here, you're speeding up. Okay? What does slowing down look like? That. Okay? Okay, I'm going to do a couple here that are tricky. I am going to, in this pale blue line, I'm going to do a line like this. I want you to think about what that means. What does that mean? I'm going to have to extend my axes here. There we go. For that one, guys, you're speeding up in the opposite direction. Notice we're getting farther away from zero. We're getting more and more negative. You're going faster in the opposite direction. Okay, so this is speeding up in your opposite direction. Okay? I'm going to add a pink line. What is that pink line? Slowing down when you're going the opposite direction. Notice we're coming closer to zero. We're approaching zero here. Okay? So that is slowing down when you are going the opposite direction. So when you're going, say, west, if forward is east. Okay? Okay. Now, as we talked about earlier, we got slope and area. So on this, our slope is going to equal velocity over time. What does velocity over time equal to? Acceleration. Okay. Let's look at our area. Well, velocity times time. What's velocity times time? Displacement. Okay, or distance if it's going to be scalar. Okay? Okay. So we've got that. And then, ladies and gentlemen, this one for a uniform motion. Acceleration time graphs. What would uniform motion look like? Flat line. Where? On zero. Okay. If you're not accelerating, you got zero acceleration. If you're moving at 5 meters per second, your acceleration is zero. Okay. If you are accelerating, you're going to look like that. Okay, so really the only two lines I really want you to know about for this particular graph. We do not use slope for this because these are slopes of 0. Okay, a slope on this would be showing the changing in acceleration, and that's not curricular for Physics 20. And the next thing we have, area, acceleration times time. Well, what would you get for A times T? Speed. Okay. So, ladies and gentlemen, that's your video. This beautiful, beautiful, beautiful study page here has all of the stuff that you need to know for graphs on here, labeled out on a single page, ready for you guys to study. And remember the strategy, guys. I'm even going to write this down, okay? Your strategy. That's an E. However you spell strategy. I'm not an English teacher. I don't know how to spell. Can't be good at everything, and I'm not good at spelling. So for your strategy, ladies and gentlemen, you are going to read the graphs. Okay, that's your biggest thing. If I want to say it in a nutshell, read the graph. Look at those axes. Okay, the first thing you're going to do is look at those axes first. Okay, look at the axes first and use that info to help you interpret your graph. Okay, read the graph patterns and read that data. Okay, I know it's not an easy skill to learn. I know it's tough, and I know you may be feeling like you're drinking out of a fire hose, but you can do it. Do your best with it. Practice doing this, and it'll make your life way easier. Okay, I promise. It's so much easier than just memorizing this whole sheet with no context. All right, guys? Okay, so I hope you guys have a good rest of your day. No fires, injuries, or explosions. Avoid rampaging viruses. And I will see you guys next time. Now I can't find the stop button. You'd think with all the videos I've filmed by now that I would get this down. All right, bye, guys.